All right, in the past couple videos we've been talking about the beginnings of redox reactions, how to balance them. We need to start working towards the idea of how voltaic cells work, how batteries function. Basically how we visualize electricity using chemistry is it's a battery. Okay, and there is this concept that is always introduced in like chapter 4 or 5 of textbooks. I'm labeling it chapter 4 because that's what my textbook was, called the activity series of metals, and literally introducing it way back in chapter 4 makes no sense at all, so I literally skipped the topic because it only makes sense once you get to this chapter. I don't necessarily need you to memorize this, but we need to understand how it works. It's literally just a big list of metals, so I'm going to write it vertically because it takes a lot of space. Hopefully it fits on the camera okay. So, I do not need you to memorize this list. Okay, so we have potassium, calcium, sodium, magnesium, aluminum, chromium, zinc, iron, cadmium, nickel, tin, lead, hydrogen is counted as a metal. I've always visualized hydrogen as a metal, copper, silver, mercury, and gold. Okay, so it doesn't even all fit on one screen. That's okay. So this is the giant list. Now what we have is a giant list. So what does this mean? Obviously this has no relationship to the spacing of these things on the periodic table. I mean, I guess sort of. These first 4 are kind of all in this area over here. Then we have like aluminum, then we have chromium, I'm trying to do this on the screen, then zinc, then iron, then cadmium, like they're kind of all over the place. And then we have like lead, then hydrogen, then copper, silver, mercury, gold, like all in that kind of region. So the problem is it almost seems random, and as far as I'm concerned, it kind of is. But here's how this works. I'm going to write a statement and we'll kind of talk through what this means. This is just straight out of the textbook. But a metal will displace from solution the ions of any metal that lies below it in the activity series. So that sounds probably super confusing. The gist of this, the best way to interpret this is the top of the list, these things are more likely to be dissolved. I'm gonna write this sideways here. Okay, so as you go up the list, these things are more likely to be dissolved, and the things at the bottom of the list are less likely to be dissolved. Okay. So here's an example. If you take magnesium solid, which is pretty high on the list and really likes to be dissolved, and you throw it into a solution of copper, which is towards the bottom of the list. So the copper is already dissolved, it is aqueous. What will happen is the mercury, or sorry, not the mercury, the magnesium, oh yeah, this has to have a charge. This is dissolved as copper 2+. This thing will give up 2 electrons and become magnesium 2+ aqueous. It will happily dissolve. We said these things at the top are more likely to be dissolved. In order to dissolve, it has to form charges, which means it has to get rid of electrons, and the things at the bottom are happy to receive these electrons and become a solid. Okay, so what we've done is we've taken 2 things on different spots on the list. The thing at the top of the list, if you throw it in as a solid metal into a solution of something below it on the list, it will replace it. In other words, it will dissolve and the other thing will become a solid. That's what this statement means. Okay, the opposite of this is not true. So if you take copper solid and you throw it in a magnesium solution, you get no reaction. because between these two between these two elements, this is more likely to be dissolved, and this one wants to be dissolved, this one wants to be a solid, and it's already there. So there's no reason for it to react. Up here, they're kind of in, this is a solid and it wants to be dissolved, this is dissolved and it wants to be a solid. So they switch, okay? This is literally the driving force of how batteries work, is this exchange of electrons, okay? So pointing this out here, magnesium loses 2 electrons to the copper 2 plus. And so the result is that this is losing electrons, it's being oxidized, and the copper is gaining electrons, it's being reduced. So the things at the top are more likely to be oxidized. I guess we could phrase it that way too. Do it that way also, I guess. And the things that at the bottom are more likely to be reduced. Okay, this has some real-world applications. This is why things like potassium and sodium, if you throw them in water, just like solid metal, it will burst into flames. It violently wants to form the ion. And so it'll literally so violently react, it'll so happily give up its electrons that this thing literally will burst into flames. It will burn water to make this happen. Whereas things at the bottom of the periodic table, like lead, we used to use that for plumbing. It's a little toxic, so we don't use it anymore, but like the word plumbing, and this is used, the Latin word is plumbum. The reason it was used for plumbing is because it didn't dissolve. It was happy to sit there and just do nothing, okay? This is why jewelry is made out of copper, silver, and gold, because these things don't dissolve. They're happy to be solids. So if you had a ring made out of, sodium and it rained, or if you were sweating, your hand would literally burst into flames. Whereas if you have a ring made out of silver or gold, you could probably dunk it in hydrochloric acid and the thing's just gonna sit there and ignore it. It's literally gonna do nothing, okay? So this concept is pretty essential to a lot of things that we do in chemistry, but it hasn't really had any meaning. There's been no reason to even discuss it until we get to this chapter. So again, I don't need you to memorize the list, but I do need you to understand the concept. All right, thank you.